Right. So this is the tree that we have. We always begin our search from the root, right? So we start the traversal with the pre-order traversal, right? So the thing to keep in mind is that for this 3 different traversal, it's really the plan at the time when you put down the visit, right? In this case, we start our visit from F. So we put down F first, right? And immediately we visit that because it's pre-order, right? And then the recursive call order is always left, followed by right, right? So from F, you go to B. And the moment you enter B, you immediately visit the value. So you put it down. And from B, you go to A, right? Again, immediately you put it down. At this point, you see that you are going to try recursive call to left, nothing. So you return. You try the recursive call to the right. Again, nothing. You return. So at this moment, you declare that node A has been done, right? So you're going to return back to B. And from B, you're going to go to D, right? So this is the node that has not been visited yet. So you'll put down its value. And from D, you go to C. Again, you put down the value C over here. And then you're done. This is the leaf node. So nowhere to go. So you return back to D. And from D, you go to E, right? So now this is actually the end of your left tree. You try left, you try right, nothing here. So you return back to D, return back to B, return back to F. So now you're ready to explore the right-hand side. So from F, you can go to G. From G, you'll try left first, but left is nothing. So you go right, which is I. And then from I, you go to H. And this is the termination of the traversal, but not the end of the calling sequence, because you still have to follow the same route that you actually come here. So from H, this is the termination. You go back to I. You're still going to try right, but right is empty. So you terminate I, you go back to G, you go back to F. At this point, then the whole traversal will end. Okay, so this is the pre-order traversal. You do the visitation, you write down the value before you recursively go down to the lower level. Okay, so in-order traversal is actually very similar. The major difference here is that the moment that you're going to put down the value and treat the node as visited is when you have exhausted everything to the left. You cannot go left anymore, or left return like because it reached the base case, which is the num, right? Then that's the point that you can write down the value. So we still start with the root node, which is F. You'll try to go left first. This is your left recursion. So from F, you go to B, and from B, you go to A, right? And from A, you're going to go left, but left is empty over here. So now you return. This is the moment we're going to put down A's value, right? So now you return, you finish the visitation to A, right? Because after that, you'll try right-hand side, but right-hand side is also empty. So you return back to A, and then the whole A is done. So then we're going to return back to B over here, right? So when we return back to B, from B's perspective, left branch is done, right? So we also will be putting down B's value. And from B, we're going to go right and then go left, right? So again, C is the node, that's the leaf node. So we can put down the value. We return back, then we can put down B's value, and then we go right. We will put down E's value, right? So again, the whole branch is done. So we go back from E to D to B, and then to F, right? So at this point, then the whole left tree of F is visited. So we can put down F's value, right? So this is actually the left tree, right? So, and this is the root node, the original root node. So now we are ready to explore the right-hand side, right? From F, we go to G. For G, we're going to put down the value immediately because there's nothing to the left-hand side of G. And then we go to I, we go to H. And from H, again, you cannot go left, you cannot go right. So you put down H's value. Then you return back to I, right? And this is the termination of the traversal. You have all the nodes already, right? And then you back to G, back to F, and you terminate the traversal process, right? So this is your right-hand side. Okay, so if you look at this whole sequence, you'll discover that This is one of the very important property of the in-order traversal, right? This tree on the left-hand side turned out to be a binary search tree. Although this is not a prerequisite, it can be any binary tree, but it just so happened that this tree is the binary search tree. And this is how in-order traversal under this kind of circumstances will be very useful. Because if your tree is the binary search tree and you think about in-order traversal, you always try to go left before you do the visitation, and then you go right. So that's why if you look at the sequence that you produce, it's always sorted, right? If your tree is a binary search tree, then in-order traversal will be the way that you're going to use to extract the sorted sequence. All right, so very important property, although this tree traversal actually achieve the purpose, which is to ensure that for each and every node, you visit that exactly one time. But in-order traversal play a very special role in that, right? Extracting the right sequence for you. All right, so this is the in-order traversal. Finally, we have the post-order traversal, right? So again, very similar to before, but this time just keep in mind, you have to finish left, finish right, then you can do the visitation, right? Starting from the left-hand side, you're going to go all the way to the left, right? F, B, and A, right? And from A over here, you're going to have like you have no left, no right, right? So this is essentially a leaf node. So you can put down the value of A immediately. And then after that, you return back to B. Essentially, you will be looking for the next leaf node in the sequence. You go back to B, and then you go to right-hand side, which is D. You go to C, and then at C, you're going to do the visitation, right? Because it's a leaf node. And then you return back to D, you go to E, right? So E is another leaf node, so you visit. When both C and E are visited, then you will go for D, right? Over here. And when D is done, then you return back to B. We put down the visitation to B. And we go back to F. From F, we go to G. Again, left-hand side, nothing. So we continue to go right, go left, left and right, and then we put down H. From H, we go back to I, right? You try right, no right, so you visit. And then you visit back to G and visit that. Finally, the final node will be always the root node for the post-order traversal. Because at this point, it's only until the last visit, then the left-hand side tree and the right-hand side tree will be considered as visited. Okay, so this is a very important property of the post-order traversal, right? Because if you pick the last node, this last node will always be the root node. And if you walk back from the last node to the first node, you just look for the first instance that the value is actually smaller than the root node, right? For example, G, I, H, they are all greater than F, right? Which indicates they have to be continuous, right? Because they all come from the right-hand side of the tree. But the moment you encounter the first value that's smaller than the last value, which is the root value, this is indication that this is the beginning of the left tree. If the tree that's produced in this post-order traversal is a binary search tree, then you will always be able to use the last node to divide all the elements in front of you into two parts. The part that's greater, which should come first, and the part that is smaller, which should come as the first part. You can always do that, and you can recursively do that. So you take the last value, and you will give you this nice separation between left and right. If you take the last value again, which is G, again, you can actually separate like the value. In this case, once you pick G, right, both H and I, they belong to the right-hand side, right? There's no left-hand side. And here is also the case, you pick the last value, you go all the way, you will see that this is the right-hand side, and this is the left-hand side. And again, you pick D, this is the root, then you have your right-hand side, you have your left-hand side. So this principle, again, recursively applied, right? So for a given post-order sequence, you can actually very easily compose, just following this observation over here, to compose a function that uses particular principle to check whether or not the sequence is coming from a binary search tree. Okay, so this observation will be useful later when we solve one of the tutorial questions, okay? Because you're being asked, how do you recognize whether or not a post-order traversal is coming from the binary search tree, right? And this observation will help you address that. Okay, so this is the tree. So we should have the pre-order, post-order, and also in order. Start with pre-order. We immediately visit, right? So we start with 34. Go left, we have 55. Go left, we have 9. Go left, we have 59, right? And then we return. We go to right-hand side, 74. And then from 74, we go to 12. So now we return. Then we go right, 68 is not visited yet. And then we go left and right, which is 4. So this is the end of the left branch, right? So we return back to 68, to 55, to 34. Then we are off to 43. And then we just follow the sequence, right? 94, 60, 36, right? So I think pre-order is actually pretty easy to handle because the moment you are on this node, immediately you can write down the value. Okay, so in order, you have to do it with slightly more care. Right, this one, you see that this is actually a general binary tree. It doesn't fulfill the requirement for the binary search tree. So you have to really track the progress. Again, 34, you go all the way down to 59. This is the very first node. You don't have left, right? And then you return back. 9 will be visited. And then you go right, left, and then 12. Return back to 74. And you return, you do 55. And then you go right-hand side, right? Again, over here, 68 doesn't have left, right? Which means that you will try left, nothing, you'll return, and then you will visit 68. And then you will do 44. So at this point, the whole left branch is done. So you'll return, and then you go to 34. And then you go right, 43, again, you visit because there's no left, right? So do 43. And then go 94, 60. Again, you visit 60 because there's no left, right? And then you go 36. From this point, again, return back. So now we can do 94, finally. And this turned out to be the last node of your traversal. You return back to 43, return back to 34, and you terminate the whole process. Right, so this is the in-order traversal. Finally, the post-order traversal, right? Still very similar, but we just need to make sure that we will only write down the value when both child has been visited or missing. So the first node is always to go all the way to the left, but put down the very first leaf node, right? Which is 59. From 59, you return back to 9, right? This time we probably need to keep track of the other value. You go back to 9, you go to 74, 12, you cross it out. This is 12, right? Return back to 74, again, visit that. And then now you can visit 9. Go to 55, 68, 4. Again, this is the leaf node. On leaf node, you go to the parent node, 68, also visited, and then 55. Okay, so at this point, this is done for the left side. So we move on to the right side, 43, 94, 60, 36, right? The first leaf node on the right-hand side got visited. Return back to 60. And then you just follow the sequence up, right? 94, 43, and finally the root node, which is the 34, right? So at this point, then we are done with the whole post-order traversal, right? So here you can see that the property we observed previously for the binary search tree doesn't apply anymore because we do not have the binary search tree property, right? So last exercise is this 3 different BSTs that we mentioned. Of course, we have just seen how you can actually verify the solution by using the test code that's provided. But here we just do one very quick run by hand, so you cannot see how it goes. All right, so we start with BST1. This is the incremental creation, right? So the very first node that we encounter will serve as the root node. So that will be 55. And then following that, essentially we just repeatedly run the binary search. It's just that whenever the search fails, that would be the place that we should insert the element that's coming in. The second element is 4. So we'll do a search. From 55, you should go left, but left currently is empty, right? So that should be the place that we put down the value 4. And then 23, also the same, is smaller. So you go left and then you go right, right? So this is 23. And then 21, also the same, go left, go right, go left, 21. And then 12, you go left, you go right, you go left and left, right? 12. And then 7, also the same, right? You go left, right, and then left, 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 right? 7. 66, this is greater. So we go right-hand side. And then we have 1, which is smaller than 4. So we put it down here. 91, greater. 44, right? Again, should be left, right, 44, right-hand side, right? Okay, so this is BST1 following the binary search procedure. BST2 is actually very similar. We just follow exactly the same process, just repeat it one more time. 23 is the node that we have. And then we have 7. We have 66. 55, you go right and then left, right? 55. 12, you go left and then you go right. 91, right and right. And then 21, right? You're going to go left, right, and then right, 21. 1 is just left and left, right? And then 4 will be left, left, right. Finally, 44, you go right, left, and then left. Okay, so this is the shape that we have seen previously, much more balanced than before. So the last tree is the BST3, right? So based on what we have seen previously, this should be the tree that with the worst performance, because in terms of the height, it will be the greatest. And the reason actually comes from the choice of the root node, right? You see that actually the moment you pick a root node, you pretty much decided like how the tree's layout will be like. In this case, the reason why this 1 is really bad is that you look at the value, 1 is actually the smallest of the whole sequence, which means that when it comes to the distribution of the element, all the rest of the element will have no hope of going to left. You can only go to the right-hand side, right? So as a result, by choosing 1, you already decided that it is impossible to divide the element. Okay, so this is 1. And then the second element also have similar reason, right? You are picking the largest element. So now if you look at the rest of the element, now it's impossible for you to insert any element to the right-hand side because 91 already is the greatest. All right, so we have 7. 7 is right and then left. And then we have 55 will be right, left, and then right. And then you have 4, which is right, left, and left. And 44, right, left, right, left, 44. And then we have 12, right, left, right, left, left, right, 12. 23, you also follow the same route, right? Go all the way down here, but it's greater than 12. So you put it on the right-hand side of 12. And then 21, go all the way down until you reach 23, and then you put on the left. Finally, 66, right? It's going to be right-hand side of 55. Right, so it's almost like a straight line, except right, you probably have this branch off over here, branch off over here, but the rest is pretty much a linear line. So very inefficient in terms of the space. You have a lot of vacancies. So if you count the height, for this one, the case of BST1, the height will be 1, 2, 3, 4, 5, 6, which means that if you are conducting any binary search within this tree, the maximum elements that you can compare to is 6 elements, right? So that represents your complexity actually. And for BST2, this is the most balanced tree, right? And the height is also the smallest as expected. It's going to be 1, 2, 3, 4. Okay, over here, right? Which is slightly better, but BST3 is definitely the worst, right? If you do a count, it's actually 1, 2, 3, 4, 5, 6, 7, 8, right? It's twice the amount of the BST2, although the element that we store inside is exactly the same. All right, so this is the reason why picking the element when we create the binary search tree will be crucial, right? If you have a pool of element, it's already there, and you want to use those pool of element to generate a binary search tree, not all sequences are created equal. Right? Some sequence definitely will produce much better shape for the future performance. And the rule of thumb is that always, if possible, right, try to pick the element that's at the around the medium place, right? Because if you pick that, roughly speaking, half of the element is smaller, and then another half of the element is greater. If you want to create a tree that's very balanced, close to perfect binary tree, this is what you can do, right? Always pick from the remaining element, always pick the value that's closest to the median. Okay, so that will be, I think, one trick. Then the tree will be more or less balanced, right? The shape-wise will look much, much better. Yeah, this is checking whether or not a given binary tree is the binary search tree, right? So this is the direct application of the BST principle, right? But there's one thing that you have to keep in mind, right? So here we say that, okay, based on the BST principle, you have left tree, and you have a right tree, and you have your root value. Here is the root, right? You have to ensure that essentially everything, not just the immediate child node, right? But everything inside the left tree must be less than the root. And then everything in the right tree must be greater than the root, not just the child nodes over here. And this is important because if you can totally imagine that you can have a one case, like for example, you can have 5, you can have 3 over here, but inside, let's say this particular subtree, right, you can hide a number that's very large. So if you look at this subtree, which is rooted as 3, I mean, nothing is violated because 100 is indeed greater than 3. So it's appearing at the right-hand side. But if you look at the whole tree, right, which includes 5 over here, then this is invalid because in the first place, 100 should never go to the left-hand side. Okay, so this is the reason why when we do the check, you have to ensure that all the value in the left-hand side will be actually smaller than the value at the root value. There are multiple ways where you can ensure that. You can, for example, try to calculate the smallest value and the largest value in the left-hand side and the smallest value in the right-hand side. And you want to make sure that the greatest value in the left-hand side is always smaller than the root value, right? And the same goes for the right tree. If recursively that is the case, then this particular condition is true for each and every node, then we can declare that this tree is indeed a binary search tree, right? So this is one way, definitely. You just try to identify what is the smallest value to the greatest value to the left-hand side and the smallest value to the right-hand side. And you gradually work up to make sure that the root value satisfies that requirement. Okay, so the method that we provided is actually also inside the complex file, right? The way we do it is through the housekeeping of the min value and the max value. Initially, we set it to be small, very small value for the minimum, very large value for the maximum, practically indicating that there's no limitation as to what the root value should be, right? So when you first make the call to this function, we assume that the minimum value and the maximum value are essentially unbounded. It can be, your root value can be any value, right? There shouldn't be any limitation at all. So we have the following 4 different base cases. One success, and then 3 others are failures. So if you have finished your recursion and the root value finally equals none, then nothing to check. We simply return true. This is our termination condition, right, for the recursion. And then these are the 3 potential ways where you can fail the test, and in which case you can immediately return the false results, right? The number 1 condition is that if your root value falls outside of the permissible range. Later we will see that how the max and min are to be updated, right, as you go down the recursion. But here just treat it as almost like a given guideline. Right? When we check the root value, it should never go out of range, right? And this range actually are being set because, right, this node may be residing underneath some other nodes. For example, if you go to the previous example here, right, you have 5, you have 3, then when you go to the left-hand side, 5 should be your upper bound. All the value inside the subtree should not have value that's greater than 5, right? This is how we actually set the upper bound and lower bound. Okay, so if we look at the left-hand side value, suppose it is greater than or equal to the root value, then we'll return the false results, right? Here we include the equation, equality over here, because again, for the binary search tree, you shouldn't have duplicated value. But if what you have is a general binary tree, this is actually possible. I can actually stuff any value inside. The whole tree can be 1, for example, no problem, right? So that's why over here, we want to ensure that the left-hand side of the value is never greater than or equal to the root value, right? So if that happens, we return false. And the immediate right is also compared against the root, right? Immediate right should never be less than or equal to the root value. If that happens, again, this is the final failure that we can actually anticipate. So this is the base case, 4 different base case. After we have said that, this is the final crucial step, right? To do the reduction step. You can do the reduction step to the left-hand side, and you also have to do the reduction step to the right-hand side, right? So exactly the same condition should apply to the left tree and also the right tree. When we go to the left tree, right, it means that the root value must be the maximum. Root value minus 1 actually should be the maximum of all the value that's inside the left-hand side, right? So we effectively use root minus 1 and treat it as the upper bound. All the value inside the left tree cannot go over this max. And this condition is being ensured by this base case over here, right? And when we recurse to the right-hand side, then the root value will become the lower bound, right? Root value plus 1, right? Your right-hand side can never fall below this value. If you fall below this value, it means that you are violating the binary search tree property that we impose on the binary search tree. Okay, so eventually you can see that you're going to reach the case where your root to the left or root to the right are actually empty, right? So in that case, you're going to terminate with true, and nothing wrong happened over there. Then the 3 fail case, you want to ensure that for each and every node, you will never encounter this kind of case. Okay, so this is the design. You can give it a try. So we have a couple trees that we have created. You can create, for example, binary search tree tested. Then you can test it against other sequences to see whether or not this particular function can help you detect whether or not the tree is a binary search tree. Okay, the final part, which is I think not as exactly, but we should. I mean, now we are week 7, right? So we should be pretty proficient at designing algorithm, and then at the same time, after you finish, you should also analyze your performance, right? So if you go back, although the question didn't really ask for that, but you should actually look at this design and try to see the complexity. And the key over here, right, is to recognize that the recursion will only happen when your left is not empty, right? And your right is not empty. And for each and every node, you'll try to branch out. You'll keep branching out until you reach the leaf node. Your left or right are empty, then you're going to return. So that means for each and every node, you're going to do exactly one check. Actually multiple check, but in this case, it's going to be like 1, 2, 3, 4, like 4 different potential checks that you have to go through. But that is a constant number. Doesn't really change like throughout the whole of the tree. So if you have n nodes inside your tree, every node will have one chance, exactly one time, to be processed over here. So every node will be processed one time. You never miss. You never have any duplication, right? Because it's a tree. You always go down, right? So you never visit the node for the second time inside the function. So if you have n nodes, you're going to process it exactly n time. So your complexity because of that should be O(n).